The next step is to inform our boid agents about the neighbors. One method that we define to do that is get neighbors. That takes in an array list of agents or boids, and these boids will be filtered and be identified as the neighbors of this agent that we are talking of. Now, array list neighbors will be our return list of this function, and of course it's empty at the beginning. Then for each of those neighbors we have to compute the location difference between this boid that we are looking at and this other boid. So we initialize that vector, and then we iterate through all the boids. So we retrieve boid b equals boids get I. You've seen this many times by now. And then we compute the location difference between this other boid and myself. So we set the location difference to the other boid's location, and then we subtract our own location. And now, and then we can test whether the location difference between me and the other boid is greater than some perception distance. If it is greater than my possibly perceived distance, then this boid is not a neighbor of mine. Of course, we have to define perception distance somewhere, and we define it as a global variable in this case. Perception distance can be something like 30 maybe. That's defined. Two other global constants: perception angle, that defines the angle of my perception field. That could be pi, meaning half a circle, could be something else. Let's leave it at that for now. Then we have something called a perception minimum distance constant that will inform our agent if other neighbors are too close and it needs to separate from them. So we have these few things. Oh yeah, and of course back in our neighbor filtering method, we can always rule out that the other boid that we are looking at is a neighbor if it's myself. If this other boid that we are looking at is identical with this agent, then it's obviously not my neighbor. Continue, and we can just jump into the next boid agent. Now we have checked the location difference between this agent and the other one, and the next thing that we do is we check whether the angle between this agent's orientation, which is identical with its velocity, and the other agent's location difference is greater than the perception angle that we've just defined, because then we know it's outside of our perception angle. It's maybe behind us and we don't see that far around the corner. Then we can also rule out that this other agent is actually a neighbor of us. So we continue. We ignore that one too. And all the other neighbors are both within our perception angle and within our perception distance, and it's not myself either. It's not this agent, so we can add it to the neighbors list, add b. At the end of this function we return the neighbors list, and we are done with that. Now, based on that neighbors list, we want to inform not only the acceleration of the boid at each point in time, but also its velocity and its location. So we define a general update method that takes all these things into consideration, and which receives an array list of neighbors as a parameter. And in addition to a location difference vector, which is exactly the same as the one that we've just used, we will need a velocity difference vector in order to compute an alignment urge vector, as well as a cohesion urge vector and a separation urge vector. And these three vectors in turn will inform the acceleration of our boid, and the acceleration will update the velocity, velocity will update its location. Now let's compute all these boid urges, these three ones here, and step through all the neighbors that we perceive. So once again, we step through all the neighbors in this case, and our boids, all neighbors are boids too. So boid cast neighbors get I. Then we compute the location difference and the velocity difference. Location difference, just like before, set it to this other boid's location, and we subtract our own location. Then we also compute the velocity difference, which works the same way. We set it to B's velocity and subtract velocity difference, subtract our own velocity. Now we add the velocity difference vector to the alignment urge. We add the location vector to the cohesion urge, location difference vector, and if the other boid is too close to this boid, so if location difference magnitude is smaller than perception minimum distance, then we want to actually add the location difference also to the separation urge. Location difference. Now we have computed all those three vectors, but we want to normalize them to an absolute value of 1. If they are not 0 by any chance. If they are 0, then we leave them at that value. So if alignment magnitude not 0, let's say greater than 0, then we normalize alignment vector. And we do the same with the cohesion vector. Cohesion gets normalized and separation gets normalized as well. Now, finally, we want to assign different weights to those urges. So we multiply them by some constants, some weights that we will also globally define in a second. Alignment weight is the scalar multiplied to the alignment urge. Cohesion multiplied by cohesion weight, of course. Weight and separation multiplied by separation rate. At this point in time, we have all those vectors and scaled and normalized and scaled as we want them, so they can now inform the current acceleration of this boid. So we set it to for example, alignment to the alignment urge, and then we add to this acceleration the cohesion urge, and we subtract from this acceleration vector the separation urge, because it has to go into the other direction. Excuse me. We add that acceleration vector to the velocity of this boid, velocity add acceleration. Of course, that's kind of an integration with integration step size 1. You can do that in a more elaborate fashion if you want, but for this example that shall suffice for us. And then we do the same for the location. We add the velocity to the current location, and that's it. Now we haven't defined those alignment, cohesion, and separation weights yet, so let's just quickly do that. Alignment weight can be 1, for example, and I copy and paste that just quick. For the cohesion weight can be a bit less, and then we have the separation weight, which should be really small because it impacts our simulation quite a bit. And now we have defined an update method that depends on the neighbors, and we have a get neighbors function that returns all the neighbors and filters down the general neighbors list. So what we have to do before we render our boids, we have to update their location, etc. And this update depends on their neighbors. Get neighbors, and get neighbors takes as arguments all the boids in the system, and that shall be it. Now let's click on play. We have some errors here. What does it say? Unexpected token. Maybe I have too many brackets here. If p vector blah 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 greater than perception. Yes, too many brackets. Something else is wrong. Separation. Yeah, we have a typo here, so let's fix that. And now it's running, and as you see, the boids cluster. Let's run it again. The boids cluster and then they flock away because there is no limitation to the acceleration vector or the velocity vector of the boids, but you can do that as you will.